Puma is a fully decentralized, uncertainty-aware, multi-agent trajectory planner. Our contributions include the Puma Trajectory Planner and an image segmentation-based real-time frame alignment pipeline. Our work is a first to demonstrate fully decentralized segmentation-based frame alignment in real time for UAV flights. We first introduced the Puma Trajectory Planner. Puma has three key features: uncertainty propagation, implicit obstacle tracking, and safe unknown space navigation. Our uncertainty propagation leverages the linear Kalman filter and the FOV-dependent covariance. As you can see, uncertainty about the dynamic obstacle is propagated into the future based on the LKF and is used to inflate the boundary box for collision avoidance. We formulate the optimization problem in a way that reduces the uncertainty if an obstacle is in FOV, encouraging the agent to track obstacles if necessary. However, always tracking obstacles could lead to dangerous behavior. To overcome this challenge, we introduced implicit obstacle tracking as well as unknown space-aware velocity constraints. This encourages the agent to consider the direction of motion, not just obstacles. Our previous work, Panther, uses explicit tracking, meaning its optimization explicitly states to track obstacles, whereas Puma uses implicit tracking, resulting in safer unknown space navigation. As you can see, Panther always tracks obstacles, resulting in flying backward and paying no attention to the direction of motion. In contrast, Puma balances obstacle tracking and direction of motion, leading to safer flight behavior. Now, we describe our image segmentation-based real-time frame alignment pipeline. Our pipeline uses an image segmentation approach, specifically the segment anything model, and runs data association to correct image misalignments caused by onboard localization errors. Our pipeline first takes raw images provided by a camera and distorts them. Then it runs an image segmentation algorithm to extract object features from unstructured environments. The pipeline then computes centroids for each object and filters out excessively large or small objects. Finally, it maps each object onto a 2D map, and it performs map alignment with other agents. First, we demonstrate our implementation in simulations. We flew two agents in a circular trajectory, using pads as objects on the ground. Each agent has a downward-facing camera and performs image segmentation and map alignment in real time. We artificially introduced 1 meter constant drifts in X and Y. On the top right, you can see the pipeline finds frame alignment and estimates the drift successfully. Now we test in a more challenging environment. Instead of constant, we introduced the linear drifts in X, Y, and yaw, and flew two agents in a partially overlapping circles. This makes it harder to perform frame alignments since they have fewer commonly visible objects. Despite the challenges, our pipeline successfully estimates the drifts. Finally, we test our pipeline while flying Puma as a trajectory planner. Puma is given waypoints to fly across the space while avoiding another agent and dynamic obstacle that follows a predetermined trefoil trajectory at the center. Also, we use random objects like microwaves and desks for landmarks, making it much harder to perform mapping. As you can see, despite the dynamic trajectories generated by Puma, the pipeline eventually found a frame alignment. Note that it took 80 seconds to establish alignment. However, once established, it consistently finds alignment. We also tested our pipeline in hardware experiments. We flew two agents equipped with Intel NUC and Intel Real Sense in a circular trajectory and performed real-time image segmentation and frame alignments. As described before, the pipeline takes raw images, runs the image segmentation algorithm, creates a sparse map, and executes frame alignments in real time on board. Our code is available on GitHub, and the paper link is provided in the video description. Please check them out. Thank you.